All right, so today is Wednesday, March the 6th, and today's class we're doing over Zoom. All right, so a couple things I want to get started with before I start with the slides again. I do want to go over the sampling distribution example that we did with the playing cards, where we had 12. I think most of you were there. The last class. We had 12 of you, and we came up with a sampling distribution. 5 cards each for each person, randomly selected from the 52 card deck. And so anyway, I want to show you what I came up with the calculator. So I'll share the screen with you. All right, can everybody see this? Just put a thumbs up. Let me know that you see the screen. Yes? Okay, good. All right. Oops, looks like more people are coming in. So let me get them in. Looks like Brianna is coming in also. And Chloe. All right. All right. So just give me a second. I just need to tip the phone as well. Keep doing this. Let me make sure I got everybody so far. Chloe, Ben, David, Faith, Joey, and Matthew, Timothy. I'm sorry. I shouldn't call you Tim. And Brianna. Okay. So what I'm going to do now is share with you the list that I came up with. I think we did one of them right at the end of the period for the sampling distribution. And in L3, in my calculator, I have the 12 means. These are the sample means for the 5 cards that each person selected. So these are the averages of those 5 cards for those 12 people. All right. So the sample size is 5, and the number of samples is 12. And I think I illustrated to you there was about 2.6 or 2.7 million possible 5-card hands from a deck of 52 cards, but we only have 12 of those possibilities. So this is not a complete sampling distribution; it's sort of a partial one, but it's good enough to illustrate some of the points that I was making about sampling distribution from last time. Now in L4, what I did was I entered the individual values for each of the 52 cards. And remember, an ace was 1, and of course the numbered cards go all the way up to 10. So those points are exactly the face value. And then I said a jack was 11, queen 12, and king 13. All right, so that so I entered all 52 of them. I'll just scroll down and show you what I did. So just entered 4 each for the 4 suits. All right, and then I went to one variable statistics. And in this case here, let's go to look at the population first. Population is in L4. Just hit enter. And the mean is 7. That makes sense, right? That's the one. Mean and median should be exactly the same. This is definitely a very balanced. Oops, looks like a couple people coming in. So see who's coming in now. The 3 are coming in. Okay. Oh, that's 2. Anthony and okay. Oh. All right. So we should have, and then Evan should be here in a second. All right. So Anthony should be here. All right. Anyway, so this is the population. It has a mean of 7. That would be mu. That would be the population parameter. We would use even though the calculator shows X bar, that's what the default is for our calculator, but it's a population, so we use mu. And sigma is going to be 3.742. That would be the population standard deviation. All right. Now, even though we have an incomplete sampling distribution, I'm going to show you. Let's go back to stat and show you what the numbers are for the sampling distribution. This time we know it's an L3. That's where I put it. Put L3 there. Scroll down, hit enter. And you saw this last time. The mean was 7.367, which, by the way, is pretty close to the mean of 7 for the population. It would be surprising, given this is an incomplete sampling distribution, that the mean of the sampling distribution would be equal to the mean of the population. It will be if we had all 2.6 million possible hands listed, but we don't. So, but it's pretty close. And then notice that for a sampling distribution, we're not going to use S. We're going to use sigma because it's considered like a population, all right, because the list of means is not really a sample. And notice the mean or standard deviation for the sampling distribution is 1.624. And it's less than half of the sample, or there's more people coming in. So, thought I had that before. All right. So Brad's coming in. All right. All right. Anyway, so the mean of the sampling distribution is pretty close to the mean of the population, even though it's only 12 values for the sampling distribution, and the standard deviation is lower. Excuse me, 1.624 is lower than the value for the population, which was 3.742. So the standard deviation is quite a bit lower, and the mean is approximately the same. So those are the big takeaways. Now, how about the shape? How about the shape of the distribution? So let's take a look at, and what I had to do in this case here, I had to make sure that the window for the calculator was set up properly. So I set up the window to go from 0 to 14. That would accommodate all possible values for the population, 1 through 13. And then I just set the X scale to 1. That means the distance between each notch on the graph is going to be 1. The Y I set from 0 to 12. Well, now actually I probably should probably change that. Or actually, no, that's fine. We could have that as from 0 to 12. I set that for the sampling distribution because there was only 12 possible values, but it should work also for the population because there's only 4 cards per value, right? There's only 4 students. So anyway, let's. I'm going to use do second and then do stat plot, and we haven't used this in a while, but I'll show you this. And anyway, I'm going to use in this case, the histogram, the one in the middle here. And let's take a look at what the histogram looks like for the population. So that's L4. So L4. And now I'm just going to hit graph. And as you probably guessed, there would be all these rectangles with the same height, right? There should be, how many of them? There should be 13 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 of them with a height of 4. Makes perfect sense, right? Because there's 4 cards for each of them. And this is symmetric, but it's not bell-shaped, is it? It's not bell-shaped. So bell-shaped is what we're what the central limit theorem that we talked about last time, that's what we're looking for a sampling distribution. Now let's look at the histogram for our sampling distribution. And this time I'm going to pick L3. That's where my sampling distribution, the 12 values of sampling distribution are. And then graph them. All right, so this is what the sampling distribution looks like. All right, notice that there's missing rectangles near the far end here, but that's okay. Even though this is not perfectly symmetrical, it certainly looks more symmetrical than the population does. At least I think so. You know, with real data, you're never going to get a perfectly symmetric bell-shaped curve. But in this case here, the sampling distribution definitely, and remember the sample size is only 5. If we selected a larger sample size, maybe 10 or even 20, maybe not 20, let's say 10, we would probably see a more symmetric looking, even a more bell-shaped looking histogram. But this certainly looks more bell-shaped than the population does. So with this little experiment that we did, it sort of confirms the things that I talked about in class last time. That no matter what the shape of the population is, the sampling distribution, as the sample size increases, the sampling distribution will look more and more normal. And the mean is going to be the mean of the sampling distribution will be approximately equal to the mean of the population. And the standard deviation of the sampling distribution will be quite a bit less than the standard deviation of the population. So those are the main takeaways. Any questions about that? Everybody pretty good with this? And so this was just using playing cards, and I had no idea what the sampling distribution would look like, right? Because people were selecting the cards randomly, but it certainly sort of shows you what the results would be. All right, so let me unshare this. And let's go to where we were last time with the, let me see, we were in 3.2, I think. Yeah, there it is. Was it 3.1 or 3.2? I think we were in 3.2, is that right? So let me see if I can find that. Looks like it's not there. Just give me a second here. Again. All right, so it should show up on my screen now. All right, let's see if I can. It shows up for the sharing. Here it is. Yeah. Again, a thumbs up if you can see this okay. Yes, okay, good. I think we looked at this last time, right? I think this was the last slide that last time. And what we're doing is interpreting what a confidence interval is. Remember, the level, let's go back for a minute. Let me see if I can go back to the previous slide. There we go. Yeah. Let's even go back a little further. Confidence interval. So once again, a confidence interval for a parameter. And when we say parameter, we mean we're estimating the value of the population mean or proportion. Those are the two things that we're going to be looking at in this course. So we're using sample data to estimate what the population parameter is. So a confidence interval is an interval computed from sample data by a method that will capture the parameter for a specified proportion of all samples. Now, the success rate means that for a particular sample that we have, if the true population parameter, let's say the population mean, is inside the interval, then we're successful. All right. If the true if we have a sample, we came up with a confidence interval, and if the true population parameter, like the population mean, is outside of the interval, then we're not successful. So when we say 95% confidence interval, what we're saying is that we should be 95% confident that the interval that we created from the sample data will contain the population mean or population proportion, and so we're confident that the interval that we have is one of those 95%, and it's not one of the 5%. That's basically what we mean by confidence level. All right, we're 95% sure that it's in there. It is not a probability. All right, either the population parameters in the interval or it's not in the interval. And then, here's an example here. In this particular case, 1, 2, 3, 4, 5, there were 100 samples that were done in StatKey, and I'll show you in a little while how we come up with this with StatKey, because that's one of the topics for today. And so there was 100 different, or actually looks like it's 200. I can't even read this thing too well. Yeah, it looks like 100. So the 100 samples that were generated by StatKey, and there were 5, and each of these line segments represents a confidence interval. The vertical line that goes through here is the population parameter, which, by the way, we don't ordinarily know, but for the examples we're doing here, we're assuming we know what it is. The green lines, each of these intervals contain the population parameter. So this value here, whatever this value is here, is inside each of these green lines. All right. The red lines, however, which are the confidence intervals for other samples, there's 5 of them, do not contain this value. All right. So this is an example of this. We also said that that if the sampling distribution is relatively symmetric and bell-shaped, a 95% confidence interval can be estimated using this formula, the statistics plus or minus 2 times the standard error. Now, the standard error, once again, is the standard deviation of the sampling distribution. In the example of the playing cards, that was the 1.624. I don't know if you remember that number, but when we're considering the standard deviation for the sampling distribution, that's called the standard error. And it's saying here to get a 95% confidence interval, we can estimate it by simply multiplying 2 times the standard error. That's called the margin of error. Remember, a confidence interval is basically the sample statistic, all right, the sample mean, let's say for the sample that we have, plus or minus the margin of error. So we take the sample mean, for example, and subtract the margin of error, take the sample mean and add the margin of error, and we get the endpoints for that interval. And what they're saying here is that margin of error can be estimated by 2 times the standard error. Now, that's not always true, all right, but it's approximately true if the sampling distribution looks to you to be symmetric and bell-shaped. All right, we're going to talk more about that later. And here's an example here where they're saying that the sample size for a survey is 1,502 Americans. 86% of these Americans answered a question in the survey, and they considered the economy top priority for President and Congress. That means 14% did not. And the standard error for this statistic is 0.01. All right, so that is the standard deviation of the sampling distribution, 0.01. What is the 95% confidence interval for the true proportion of all Americans that consider the economy to be a top priority? So using that estimation formula, we take the 0.01 and multiply it by 2. And that gives us our margin of error of 0.02. And we simply add and subtract that. That's 2%, by the way, right? 2% if you want to use percentages. So anyway, 86% or 0.86 minus 0.02 is 0.84. 86% plus 0.02 is 88% or 0.88. The answer is 2. 0.84 to 0.88 is our estimated confidence. And what we're basically saying here, let's do the interpretation. We're saying we're 95% sure that this particular interval contains the true population parameter. That means the true percentage of people who believe that the top priority for the president of Congress is the economy. So we're 95% sure that this interval, this particular interval, contains that true population parameter. All right, that's what we're saying. All right. Now, let's look at this particular thing here, and we look at A and B, and then C says both are true, and D says neither one is true. So let's look at the interpretation for 95% confidence. A says we're 95% sure that the interval contains the parameter, and B says there's a 95% chance it contains the parameter. So which of the, and you can unmute yourself, which of these A, B, C, or D is the correct answer for this? Which of these is true? Are both of them true? Are neither of them true? Or is this or A, or is it A, or is it just B? If anybody could answer.
A is true.
A is true. That's right. And B is not true, right? Yes.
Yes.
Right.
It's not true.
Because we said it's not a probability. See, and so it's not a probability. It is it's a confidence. It's how confident are we that it's contained there, not what is the probability that's in there. So the answer is A. B is false. And of course, that means that both C and D are false. All right. So here are common misinterpretations. This is important because this shows up on tests. Maybe the final exam, but certainly on test number 2. Misinterpretation number 1. Let's see what it says. It says a 95% confidence interval contains 95% of the data in the population. That's not what it means, does it? No, that's not necessarily true. So that's definitely incorrect. All right. Misinterpretation 2. I am 95% sure that the mean of a sample will fall within a 95% confidence interval for the mean. Okay. That's actually false because what's the answer? Think about how the confidence interval is constructed. If we're dealing with means, isn't the sample mean right in the middle? Isn't the sample mean plus or minus the margin of error? So actually, you're 100% sure that the mean of that sample is in the confidence. All right, so that's false. And let's look at 3. The probability that the population parameter is in this particular confidence interval is 0.95. We just, of course, stated it's not a probability, so that's false. All right, let's look at this one here. A 98% confidence interval for mean pulse rate is 65 to 71. The interpretation, I am 98% sure that all students will have pulse rates between 65 and 71. Is, and again, please say, is that correct? Is it true or not true?
It's true.
Okay. All students will have pulse rates between 65 and 71. Anybody else? So I'm sort of telling you this. the answer is not quite true, but anybody can give me a reason why it's not true. Or actually, was it Brianni? Brianni, were you the one who said it was true?
I forgot that the mean wasn't a part of the confidence interval,
Right.
or it's not supposed to be affecting the confidence interval.
Well, actually, the interpretation is always about the population. So what they're saying here is I'm 98% sure that all students in the population will have pulse rate between 65 and 70. Does that sound right?
No.
This is from sample data, right? And it's just, it doesn't necessarily include all the data, does it?
No, it doesn't.
Right. The minimum is probably going to be outside the range. The maximum is going to be outside the range. So, and you can't say I'm 98% sure. First of all, it sounds like a probability when you say that, right?
Yeah.
Yeah, and you can't even say that I am 98% sure that 98% of students will have pulse rates between 65 and 70. You can't say that at all. The only thing you can say is I'm 98% sure that the mean of the population inside that. That's what it means. The mean, not all the values, just the mean. That's all we're looking for. All right. So that's why it's. Let's look at this.
Okay.
A 98% confidence interval for mean pulse rate, it's the same thing. The interpretation, I am 98% sure that the mean pulse rate for the sample of students will fall between 65 and 71. Is that correct or incorrect? I think, Brianni, you're a little shy to say yes or no. That's okay. Anybody else want to say, is this true or false? Well, again, it's saying the mean pulse rate of the sample. The sample is 100% sure it's in the input. So, no, it would have to say, let's see the next one. It shows you the correct one. Yeah, that's the correct one. So this is false also. This, I believe, is the correct interpretation. I am 98% sure that the mean pulse rate for the population of all students will fall in that interval. Yes, this is the correct interpretation. All right, you see the difference between the false interpretations and the correct one. So you will be asked in testing situations, probably in the homework too, you'll be asked for the interpretations, all right? Or choose the correct interpretation, and now you know what it is. All right, and this is, of course, the review. What we said, the population, we can have multiple samples out of a population. The samples will not necessarily all have the same sample mean or sample proportion. So there's sampling, what we call sampling variability. Because of sampling variability, we can't use the mean itself from the sample, which is called a point estimate. We can't use the point estimate as necessarily as a good way of determining an estimate for the population mean or proportion. We have to create a confidence interval. The margin of error is simply a range of values in which the population could be in, the population parameter could be in. It's called a margin of error because most likely the sample statistic or the sample mean is probably not going to be equal to population. So by creating an interval, we have a better chance of estimating the population parameter. That's the whole idea. The standard error is another term here that we talked about. It's a standard deviation of the sampling distribution. All right. And just like we did with the playing cards, we calculate the statistic for each sample. We have to make sure, of course, when we do this, the sample size is the same. So we're comparing the correct samples. All right. So now we'll go to the next slide. Or let me just stop sharing here. Let's go to 5.3. Let's see if I see it here. No, 3.3. I'm not 5.3. Yeah, 3.3. Constructing what are called bootstrap confidence intervals. Now, if you took this course maybe through another professor at Rowan or maybe at another school, At this point, you would be given formulas to basically memorize and to use to create confidence intervals. And some students have no problem with it, and I have found other students get lost pretty quickly because the course moves pretty quickly, and they get bogged down with these formulas. And they really are starting to use formulas before they actually understand the concepts. So the Locke family, the 5 Locks who created the textbook and also created StatKey, came up with this idea. Let's create the software, StatKey, and we're going to simulate. We're not going to use formulas yet. We're going to simulate for the construction of confidence intervals. All right, we're going to simulate it using the software. Now, simulation just means we're mimicking the actual sampling distribution, but we're using a computer software program that allows StatKey to come up with these samples. All right, so we're not going to be using formulas yet, even though you learned one, that approximation formula with the 2 times the standard error for the for the margin of error. Don't necessarily remember, you can remember it, but it's not that important at the moment. So constructing bootstrap confidence intervals is what we're going to talk about. And I'll explain to you what a bootstrap confidence interval is in a second. All right. All right, so this is just review what we looked at before. So let's actually go to here. This is, of course, the last slide for the previous section. So when we create a confidence in a sampling distribution, it would be good if we had multiple samples, right? Multiple samples that we could use. That's how we came up with our sampling distribution in class. We had 12 people come up with 12 samples. Now, in real life, if you're doing research, you're just going to have one sample because it's going to cost money and you're not going to be able to do more than one. And that's where the formulas come in. But for the simulation that we'll be doing, we're going to create multiple samples, not through formulas, but through this computer software. And then we're going to be able to come up with a sampling distribution through this simulation software. Again, you don't need to know much about the simulation software. On the stat, and we'll go to the StatKey website in a little while and to show you how it works. But so anyway, it says here to create a plausible range of values for a parameter. Take many random samples from the population and compute the sample statistic for each sample. That's what we did in class, right? We did 12 of those. And then compute the standard error as the standard deviation of all these statistics. And that's what we did in class, right? That's what we did with a calculator. We determined the standard error from the sampling, the standard deviation of the sampling distribution. And it says use the statistic plus or minus 2 standard deviations. Well, there are standard errors. That's only for, of course, the 95% confidence interval. There could be other ones too. Now it says there's one small problem. We only have one sample. Yes, there's only one sample. So typically, this is not something people do, right? They don't have access to many samples. We only have one sample. So how do we simulate? How do we create many samples in this computer software called StatKey? How do we create many samples when we only have one? And the answer is, they say bootstrap. Now, bootstrap sounds, you probably heard the term, maybe you have. It's an old-fashioned term. Somebody, fails at something and people say, just pick yourself up by your bootstraps. And what were bootstraps? There were straps that were connected to the boots that you were wearing, and just hold on to them and pick yourself up. So it's just an old-fashioned phrase, old-fashioned term, but statisticians back then used this term to create something out of nothing, basically. That's really what they're saying here. So forget about it. It's just a term, a word. So we use this so-called bootstrap procedure. Um, now, suppose we have a sample. It says Reese's Pieces. I guess we'll look at Reese's Pieces. We know there's various colors of these Reese's Pieces if you ever ate them. And anyway, so basically, if you had 100 of these, a sample of 100 Reese's Pieces, and you wanted to know how many of them were orange, and so you counted them, right? And then you ended up with 52 orange Reese's Pieces out of 100 total in the sample. So our sample proportion is simply 52 divided by 100.52. And we use the symbol p hat for our sample proportion. So we might say, well, if we had millions of these Reese's Pieces, but we went into the factory where they created these, and we looked at, all the possible Reese's Pieces that were created in the factory for months or years, whatever. What do you think the number of orange Reese's Pieces would be, or the proportion of them would be? So we're trying to guess at that. We're trying to estimate. So we can estimate, and according to the people who created StackQ, we can estimate the variability of the statistic using only the data in the original sample. That sounds kind of odd, right? Because the variability of the population, what we found, is more than the variability in a sample, right? That's what we found out through our playing card example. So this sounds kind of odd, but let's bear with it. Let's see what they say. It says, we do this by imagining the population is many, many copies of the original sample. Oh, all right. This sounds interesting. So suppose we take our sample of 100 Reese's Pieces and we just multiply it. We just have many, many samples from that sample. We just create many samples from the sample. And then you might say, well, wait a minute, aren't we just duplicating the sample, right? Aren't we just creating, we do this 100 times, aren't we just creating 100 of the same sample? And the answer is, well, maybe not. Maybe we're going to be doing something to each of these duplicated samples. So the technique is called bootstrapping, and what we do, and just a second. Where are you? So what we're going to do, and actually I'll scroll down because I don't want to get you too confused by this. We're going to scroll down. And all right, this looks kind of confusing. So let me just, I don't want to confuse you. So what we're going to do is we're going to be sampling with replacement. So what does that mean? So they said to simulate a sampling distribution, we could just take repeated samples, and notice the same sample that that one sample. And what we're going to do, we're going to make multiple copies of it. But then what we're going to do is sample with replacement. Now, what does that mean? That means that it's possible. So let me give you the example. We had 12 possible sample means for our deck of cards, right? The deck of cards. And they were all different, but all 12 of them had different sample means. And what if we only had one of those sample means? Okay. Let's say it was the one that was 4.8. I believe that was the person out of the 12 who had the smallest sample mean of the 5 cards. And how did they come up with 4.8? Well, they added up the values of the 5 cards and divided by 5, right? But suppose we take those 5 cards and we decide to sample 5 from that mini population of 5 from the sample. And if we sample with replacement, it's possible that we may pick the same card again. All right? That's the whole idea with sampling with replacement. We put the cards back, it's possible we may be able to sample the same card more than once. All right? Which would mean that the sample mean would change. So for example, if you had ace, 2, 3, 4, 5 is your hand, right? and then you take those 5 cards and you pick a card from that sample, and then you put it back. So you record what you picked and you put it back, and then you mix up the 5 cards. You're not mixing up the 52 cards, you're mixing up the 5 cards, and then you select again. It's possible you could pick that same card again. See what I'm saying? So that's what StatKey is doing here. They're sampling with replacement. And so from that original sample of whatever the sample size was, maybe it was 100 Reese's Pieces, and there were 52 oranges in there. It's possible that we could sample, when we select 52 again, when we select 100 again, we could have maybe 50 orange, or we could have 53 oranges, because we could possibly have maybe multiple greens that we didn't have before. It's possible we could select one of these again. That's the whole idea. All right. So if it's confusing to you, don't worry about it. That's the strategy. That's what they're doing here, calling it bootstrapping. And this is how they create multiple samples. They just take the original sample, and from those values of the original sample, they create other samples that could potentially have different values and different sample names. All right. Anybody have any questions about that? I mean, was I sort of clear what they're doing? All right. They're not working with the populations unknown. They're working simply with the original sample, and they're just selecting one at a time from the sample. And each time they select something, they put it back, which means there's a chance it could be selected again. All right. You see what I'm saying? So it's possible that each sample will be different from the original sample. All right. So the bootstrap sample has an original sample and then has these duplicated samples, which may be different than the original sample. And we want to create 1,000 or 1,000,000 of them, whatever we want to, all right, of these samples. And then we create a sampling distribution. Each of these bootstrap samples will have their own sample mean. Just like, and so we'll have a sampling distribution. And notice it's done without any formulas, right? It's just a procedure that somebody came up with. Statistician came up with this procedure. This is how I'm going to create my samples. I'm going to create from the original sample, I'm going to create multiple samples, and each one of those will have their own sample mean. And then I will create my curve, or I'll create my histogram of these samples, or a dot plot, whatever I'm using. And then I can create a confidence interval from that. All right. So a bootstrap sample is a random sample taken with replacement from the original sample. It has the same size as the original sample. A bootstrap statistic, such as the sample mean, is the statistic computed on a bootstrap sample, such as the sample mean. And a bootstrap distribution is the distribution of many of these bootstrap statistics. All right, that looks confusing. Here's an example. Here's the original sample. Maybe this will be clearer to you. 18, 19, 19, 20, and 21 is the original sample. And it's possible that bootstrap sample could be this. Could be this 18, 19, 20, 21, and 22. Is that possible? Take a look at it. Here's the original sample. Could we have this as a bootstrap sample? Remember, we can only use the numbers in the original sample. So can this be a bootstrap sample? Yes or no?
No.
No. Why not?
Because 22 is not in the original sample.
That's right. You see the idea? It has to be something from the original sample to create a bootstrap sample. All right, let's look at the next one. Okay, can this be a bootstrap sample? Yes or no?
Yes.
Okay, this is tricky, a little tricky. Can it?
Oh, it can't be, because it's not the same amount as the first one.
Not the
Like
same.
there's not
the same sample size. It has to be the same sample size. It has to be, if there's 5 in the original, there has to be 5, and there's only 4. Right. Good. Very good. How about this one? Can this be a bootstrap sample?
Yes.
Yes. Because 18, 19, 20, and 21 are the values in the original sample. And in this case, instead of having 2 19s, you have 2 18s. That's perfectly possible, right? If you're sampling one at a time with replacement, you could get a sample that looks like this. And this would have a different sample than the original sample. All right, good. Now, this is where students get mixed up. You have a sample size of 50. You sample with replacement 1,000 times to get 1,000 bootstrap samples. What is the sample size of each bootstrap sample? Is it 50 or 1,000? I hope this is clear, but some students mix this up. What is the sample size of each bootstrap sample? Is it 50 or 1,000?
50.
50. Right. Each of the 1,000 bootstrap samples have a sample size of 50. The thousands referring to the number of samples that were generated by the bootstrapping procedure. Okay. All right, this is silly. See if there's anything else here that would be worthwhile. All right, let's go to StatKey. All right, so I'm going to unshare this. And the best way of learning this is StatKey. Now, by the way, when you're in StatKey, you can play with it. You can't break it. So don't be scared of it, all right? And they have videos in there that explain how it works, but I'm going to show you how it works. So just give me a second here. I'm going to open up. Oops, I can't do that. All right, hold on one second. What do I do? Oh, here we go. Here we go. All right, so let me open up StatKey. And hopefully you all remember how to get there. Just type in StatKey and you'll see it. All right, so I'm going to share this here with you, the StatKey website. And again, a thumbs up if you see it. Everybody see it okay? Yes? Thumbs up? All right. Now, the main thing that you're going to be doing with StatKey, there's many features in here, by the way. You can play around with sampling distributions, all right? And it shows you how to play, and there's, you can create an exercise for that. Maybe I'll do that when we get back from break. But what I want to show you here is two main columns that you'll be working with in this course. The middle column says bootstrap confidence intervals. And then this last one, which we haven't learned yet, and don't worry about it yet, is randomization hypothesis test. So ignore that for now. So let's go to bootstrap confidence intervals. And there are several options here. Confidence interval for a single mean. It says median standard deviation, but we're just going to look at means. And confidence in CI means confidence, and CI or confidence interval for single portion. Now they do have difference in means and difference in proportions also as part of the exercises in the homework. But that's when we're comparing two groups, all right, where we're looking at the difference in the means between, let's say we have a sample and we're looking at the mean for two groups, and we can subtract the mean and see if there's any significant difference between the means or proportions between the two groups. So that's something we'll look at also, but don't worry about it for now. So let's look at the confidence interval single mean. I'll click that. And this is what it looks like. And I'm going to show you basically what's here. All right. So the first up here where the blue is here, they have built in some data sets that are part of the course. You'll see these data sets in the part of StatKey that has all the Excel files. But here are the ones that are actually downloaded. And let me pick one. Let's see. Let's pick one, the body temperature. Let's look at that one. Yeah, this one will be good. So here's 50 body temperatures that were taken, I guess, of human beings. And there's been this, you've been told since you were young, that the average normal temperature is 98.6. But you probably know from your own experience that that's not necessarily your normal temperature, right? Some of you run a little bit higher than that. Some of you run a little bit lower, and you know that's your baseline. So everybody seems to have a different normal body temperature. So anyway, so there was a sample that was done of 50 people with their body temperatures, and off to the right here, you can see there is it says original sample. See it? And it gives you some information about the original sample. It says there were 50, and it's a dot plot. Notice there's dots there. Should be 50 dots. And the mean, the average of the 50 is 98.26. So most of the people are in this range here. And then it looks like somebody way out here. It says 100.8. That person's running pretty hot, right? I don't know if I believe that. There's somebody who has a normal temperature of over 100. But anyway, it was accepted in the data. Gives you the median also, and also standard deviation. Now, it's pointing to 98.26 here because that's the mean, all right? So this is the original sample of 50. Now, if we wanted to generate from this original sample one bootstrap sample, it's very easy to do it because we simply go down below where it says body temperature and it says generate one sample. I'm just going to generate one. Okay, and here's that bootstrap sample right here. And notice that the dot plot looks different, doesn't it? Number one, it doesn't have that extreme value here. And notice at this value here, it has many more than over here, right? So notice that this particular bootstrap sample looks quite a bit different than the original sample. And that's because we're sampling with replacement. So what is the mean of the bootstrap sample? 98.192. All right, and that's what it looks like. And notice over here, it plotted the 98.192 as a dot. All right, so the bootstrap samples will be plotted on this graph here. All right, so let's say I'm going to reset the plot, so it's going to make that disappear. Let's say I want to generate 100 samples. And what this program does, it generates them immediately for you. There's 100. And notice you have a distribution, don't you? Now, what is this one that's here? This is one of them. All right, it happens to be the one at 98.222. But if I actually move my cursor along here, notice that the bootstrap sample actually changes, right? So if I pick that one, that's what the bootstrap sample looks like. And if I move it along here, it just gives me other ones. So these are 100 bootstrap samples. What is the sample size for this, for the 100 samples? What is the sample size? Just yell out what it is. Sample size. I hope you're paying attention, guys. I know Brianna is paying attention.
100.
100 is the sample size. Who agrees or disagrees with Corbin?
Oh wait, no, I misread. Samples equals 100. It's 50.
Yeah, so it's very easy to get confused. So the sample size is 50 for each of the 100 samples. So when it says samples is equal to 100, it's not the sample size, it's the number of bootstrap samples that appear here. Now the mean is, now this is a sampling distribution, isn't it? But it's called a bootstrap sampling distribution. Bootstrap. Okay? Which means it was generated by this bootstrapping. Instead of selecting out of the population 50 each time, 100 times, what we're doing is we're taking the original sample and we're creating bootstrap samples from the original sample. And now we've generated a bootstrap sampling distribution. Now, let's actually generate more. Let's reset here. Let's generate 1,000. Oh, now it starts looking like a normal curve, doesn't it? It starts looking like a normal curve. So the more of these bootstrap samples you create, you're going to get something that looks sort of like a normal curve. All right? And what is the mean here? The mean is the mean of the sampling distribution. And the standard error, that is the standard deviation of all 1,000 means. Okay? So 98.256 is the mean of 1,000 bootstrap means. The standard error is the standard deviation of 1,000 bootstrap means. Okay? And that's what's being plotted here, are the means of each of those 1,000 samples. Everybody clear about that? And that's what we're looking at here. Now, what if we wanted to create a confidence interval from this? Now, remember, and the reason why this is done this way, because remember, confidence intervals are created from a sample, one sample. And this is a very clever way of creating a confidence interval from one sample by creating bootstrap samples. Okay? So we're creating a sampling distribution from the one sample. That means that we could create a confidence interval from this because it came originally from one sample. See something? It's a very original idea, and it works because later when we use formulas, you're going to see how well this works. These confidence intervals here come very close to the actual values of the confidence intervals when we use formulas, which is pretty remarkable. So anyway, I've generated 1,000. By the way, you can generate any number of samples you want. If I wanted to generate 1,100, I just click this one more time. Now I have 1,100. If I want to correct 1,150, I'm going to click this until I get 1,150. There you go. Now I have 1,150. See what I'm saying? You can create any number, and if you wanted 1,152, I'm going to click this 2 more times. All right? It's pretty amazing software. I've never seen anything like it, and you don't need to be a computer programmer to use it. Anyway, all right, we have 1,152 samples now. All right, and what if we wanted to create a confidence interval? Now, confidence interval, remember, it's the middle. If we remember, actually you don't, but if we were going to graph it, it's actually the middle of the graph. If we say 95% confidence interval, because this is a sampling distribution, we can actually pick the middle 95%. So the way to do that is I'm going to click this 2-tail. See, it says left tail, 2-tail, right tail. Click 2-tail here. Now, what StatKey has done here, it defaults to a 95% confidence interval. And what it means is that 95% of these dots, there's 1,152 of these dots here, right? So 95% of them, whatever that number is a number of black dots, are the ones that are inside the interval. And what's outside the interval are all the dots that are outside of the 95%, whatever that number is. So it's the middle 95%, and then we have 2.5%, which are these red X's to the right, and another 2.5% of the dots are to the left. Okay? And then down here, you scroll down a bit so you can see it better. Notice that the black dots begin at 98.059 and they end at 98.465. So through this simulation, we can estimate a 95% confidence interval. Okay, by simply clicking 2-tails here, and we have it. Now, if we were going to create this using that formula, all right, remember the formula? The formula basically was what? The margin of error was 2 times the standard error, right? 2 times the standard error. And then we took our original sample mean and added plus or minus 2 times the standard error of the sampling distribution. Well, this is our sampling distribution here. Here's our standard error, 0.105. What if we multiply that by 2? We get 0.21. And suppose we add and subtract that from the original sample mean, would we get something similar to these numbers here? Well, 0.21 minus 98.26 is 98.05. Wow, look how close that is. And then if we add 0.21, we get 98.47. That's pretty close, isn't it? And that's actually, if we round it, it's pretty much the same, isn't it? Almost the same. So the stat key gives us a way of allowing us to visualize what a sampling distribution would look like if we were actually had it. All right. So remember, this is a fake sampling distribution, but it actually works. It's very close to what a sampling distribution would look like, and it gives us an idea that it looks normal too, doesn't it? It looks like it gives us normal distribution. Now, what if we wanted a different level of confidence? This is where stat key really works, because we haven't learned anything more about formulas for different levels of confidence. What if we wanted 90% confidence? We want to be 90% sure. Let's see what happens. What we're going to do is I'm actually go and click this middle blue button here. It says 0.95. I'm going to click it, and it gives me this this little formula here, and I'm going to type in 0.90 and then hit OK. Now, notice what happens. Now we have bigger tails, so because 90% in the middle is fewer black dots, right? There's fewer in the middle and more on the tails. So what happens, and look at the interval, it becomes narrow, more narrow. It's now 98.06 up to 98.428. And by the way, that formula, that 2 times standard error, doesn't work. That's only for the 95%. Now we have a 90%. So here's a general rule. General rule. The lower the level of confidence, the more narrow the confidence interval. And let me ask you a question, and just use your common sense. Do you want a more narrow confidence interval to estimate your population mean, or do you want a larger, a longer, a wider? Which one would you prefer? What would make more sense to you? Just using logic. But do you want, if you're estimating something, do you want a narrow range of values or a larger range of values? I think the answer is pretty obvious. What's the answer?
A larger range of values.
You want the larger range of values?
A larger range.
Well, let's think about it, okay? I'm estimating something. Let's say I'm estimating my height, and I'm saying I'm anywhere from 2 feet tall to 10 feet tall. Is that useful? But what if I say I'm between 5'3" and 5'6"? Is that useful? Which one is more useful? If I'm saying I'm between 0 feet, I'm between 2 feet tall and 10 feet tall. Does that gives the person any information about how tall?
Range.
No, I'm serious. I'm not trying to be funny. If I'm saying I'm between 2 feet and 10 feet, is that information useful information to you? But if I say I'm between 5'3" and 5'7", is that useful? Is that more useful? Guys, are you paying attention? What's more useful? The Corbin, I can't hear you. I don't know what's wrong with your sound. And somebody else. Somebody else. Again, I'm not trying to be facetious here. I'm really not. But the wider all right, let me just say, the wider the interval, the less useful it is. Because I just gave you the example. If I'm saying I'm between 2 feet and 10 feet tall and you don't see me, how useful is that? You don't know if I'm really short or really tall. But if I'm telling you I'm between 5'3" and 5'7", you know I'm pretty short. See what I'm saying? So you want a narrow confidence interval. The narrower, the better. But notice what we have here. We become less confident. We're now only 90% sure. So it's a trade-off. All right. The lower the level of confidence, when we want something, if we're just dealing with level of confidence, all right, if we want something more narrow, we have to lower the level of confidence. So now we're less sure that the true population mean is in that interval. See what I'm saying? We're less sure. Now let's increase to 99%. All right. Where am I here? Here's my 0.9. What happened to the interval? Did it become narrower or wider? Look at it. The interval, did it become narrower or wider when we increased from up to 99%? The level of confidence. Now we're 99% sure.
The interval became wider.
It became wider. There's the trade-off. That's the trade-off. Now you're going to learn later that the sample size plays a role with this, with the how wide or narrow a confidence interval is. Okay. All right, everybody clear on this? And that's how you play with this. All right, and you can play with this. Now, in the homework, they might give you actually printouts of one of these here and ask you questions. Now you know how it works, right? And what is and somebody tell me what the confidence interval is in this case here. It's between which two values? I don't know. I'm wondering if there's people who just signed on and not paying attention at all here, because I'm only having 2 people who are actually answering questions. All right, that's disappointing. So we'll continue with it in class. At least I could tell whether you're paying attention or not. It's between 98.016, this is the one on the left, and 98.541. Okay. All right. All right, let's stop this and let's go back to the 3.3. We'll just stay on for a couple more minutes. Share that with you. All right, so now I just showed you how it worked. And, all right, you know what? We're going to skip a lot of this because this is all right. So anyway, golden rule of bootstrapping. Bootstrap statistics are to the original sample as the original sample is to the population. So basically, what they're saying here is when we create a bootstrap sampling distribution, it's like choosing a sample from the original population. Okay. It says the sampling distribution is centered around the population parameter. The bootstrap distribution is centered around what? Is it the population parameter? How was it generated? From what? Too much silence here. It was generated from the sample statistic, not the bootstrap statistic, because that is one of the things that was generated. The original sample statistic is the distribution came from that through the sampling with replacement. The standard error, the variability of bootstrap statistics is similar to the variability of the sample statistics. So we can have a standard error of a bootstrap sampling distribution that we can use. And this looks very complicated, but this is basically how we come up with bootstrap distributions. So the standard error is called the bootstrap standard error. The margin of error, we can use the same idea, but remember, we can come up with different levels of confidence, not just 95%. All right, and we can calculate a statistic for each bootstrap sample. All right, now we can create proportions. I haven't shown you this, but and actually, let's go back a minute. Maybe it would be better to show you stat key just for one more time. So where are these stat key? I think this is it. Oh, this is it. Yep. Now to get back to the original scroll up a little bit here. To get back to the original screen, just hit Stat key. If I want to do the same thing for proportions, I click CI for proportions. Now, you have different examples here also for proportions. So they'll have a sample size and then they'll have a count. All right, sample size and a count. The count divided by the sample size, of course, is our sample proportion. And in the same way, you'll get Bootstrap sample proportions. The same thing. All right. Now, if you wanted to create your own data, you can edit the data here. It doesn't matter where you enter, and you can enter a count and sample size. For example, if you wanted to create a sample size of 200, and you wanted the count, the number of successes in the proportion to be 50 for the sample, then you click OK, and now you get a sample proportion of 0.25. So there's a little bit of flexibility with this. You could just hit edit data and create your own example. And by the way, if I wanted 5,000 samples, I'm just going to click 1, 2, 3, 4, 5. Here's 5,000. And here's my 95% confidence interval. Okay. And notice it gives me the numbers down here. And if I wanted to create a 93% confidence interval, then I'm just going to type in 0.93 here. And click OK. And here's a 93% confidence interval. All right. So you get the idea? And you could try this also with, let's go back to the original screen. They have examples with difference in means and difference in proportions. For example, difference in means here. We're looking at two groups. We're comparing the means of two groups. So here's two samples, right? And they give you information about each sample, the sample size for each sample. It doesn't have to be the same. All right. And the means, difference in means. All right. That's what's, and then we can create, 1,000 of these. All right. And the interpretation is a little different because in this case, each dot represents the difference in means between the two groups. And it can be negative or it can be positive. All right. Anyway, that's it for today. Any questions about what we covered today? Now, we didn't cover section 5.2, which was part of the what was in the syllabus, so I will leave that off, but I did cover 3.1, 3.2, 3.3, and did we cover 3.4 at all? I'm not sure. Let me see what 3.4, we did not cover that. So we'll cover that when we get back. All right. So 3.1, 3.2, and 3.3, that you know enough now from 3.3 to do those problems. All the homework for 3.1 through 3.3 will be due not this coming Sunday, but the Sunday before you come back to school. So you have extra time for that, all right? And then what we'll do when we get back is I will go over 3.4 and 5.2 on the day we get back. All right, so that's it. Any questions about anything? And over the break, I will grade those Excel quizzes. Unfortunately, I couldn't do it over the weekend. There was some illness in my family. I just didn't have any time. So unfortunately, it didn't work out, but I will have those. I know that there's progress reports coming out. I have to deal with those also, I think next week. So I have to have everything graded by. All right, no questions? All right, guys, so have a nice break. And I will see you in class on which day is that? In 13 days, whatever that day is, or 12 days? 12 days. That would be the 18th. See you in class on the 18th. And have a good day.
Goodbye.
All right, take care. Bye-bye.
See ya.
Yes, see you. Bye-bye. Take care. And Brad, are you there? You can go off.